Hello everyone. So we already have started discussing about the physics, and over the past few days we already have seen physics associated with different types of sensors. In the last lecture we have seen what is acoustic sensing, and we have discussed what are the different geometries that we may use for acoustic sensing. It can be infrasound sensing, it can be audible sound sensing, or it can be ultrasound sensing. In many cases you will find that acoustic sensors are also used as an indirect sensor, as we have discussed for optical sensing, because for example the first thing that we discussed in the acoustic sensing lecture is the measurement of distance, or the detection of the distance. In that case, what we did was that you have a source which also have a detector. Then this source actually sends a sound signal. If there is an object present at certain distance d, this sound signal will reflect back from this object, and then we detect this reflected signal using this detector, and then we decide what is the distance between the source and the object. So this is kind of an indirect sensing. The same concept we also have discussed during optical sensing application. By indirect sensing, because our object is to detect distance or to calculate or measure distance, but what we are doing is we are using sound source in order to accomplish that. In case of optical sensing, we discussed that our target was to detect say color of a certain strip, and then we took help of optical source and we detected the reflected optical energy using a detector to quantify the change in color. So something like that, right? So today we'll be discussing a very widely used principle which is known as microfluidics in sensing. So what is microfluidics? Microfluidics is study of flows where characteristics length scale is in micron. So it is a study of flow of fluids, right? It can be any fluid for that matter. It can be a gas, it can be a liquid, but in this case what we consider is liquid. For example, say water. So if I explain the same thing in a simpler way, I can say if you have a flow of water inside a structure which is in the micron range, then whatever phenomena we see in that particular structure inside the fluid is nothing but microfluidics. So it's study of flows where characteristics length scale is in micron. What is characteristics length scale? It's the length scale over which the characteristics of this particular fluid changes. So that length scale is in micrometer. So that's why we call it microfluidics. In certain cases you will find people call it the behavior of fluids through a microchannels. So microchannels itself, the dimension, one of the dimension of this channel will be in micrometer range of the order of 10 to the power minus 6 meter. So it is defined using this particular statement. In certain cases you will find it is a system that manipulates a small amount of fluid using small channel with sizes 10 to 100 micrometers. So this is a study where you actually try to figure out how the characteristics of that fluid is changing in a very small dimension, say 10 to 100 micrometers. Another term which is related to the term microfluidics is nanofluidics. So microfluidics and nanofluidics both are to some extent similar. The only difference is the characteristics length scale. So there is a critical length scale beyond which you may not find all the phenomena that is happening in microfluidics is actually true for nanofluidics, but to some extent you may also apply the considerations in the microfluidics to nanofluidics as well. Now, the microfluidics itself is divided into various categories. For example, it can be open microfluidics, this can be continuous flow microfluidics, the same can be droplet based microfluidics, this can be digital microfluidics, this can be paper microfluidics, this can be particle detection microfluidics, this can be microfluidic assisted magnetophoresis. So there are several types of microfluidics and several types of considerations in a microfluidic discussion. So when we use the same thing for sensing applications, we'll try to find what are the different types of microfluidics that are usually used in sensing applications. In fact, you'll find all these types are used in sensing applications, but we'll not discuss all of these. In this lecture, we'll try to understand in general how microfluidics can be used for sensing applications. Now, here are the applications. This particular phenomena can be used in lab on a chip design. What is lab on a chip? Lab on a chip is a small system that you develop inside a lab which can mimic a traditional technique. So when I say a traditional technique, what I mean is, for example, you have different high cost equipments present in a big setup. Then you try to mimic the same thing in a small setup in a microfluidic channel. So this is what it is shown in this picture. For example, you have different high cost equipment, there are different excessive time and energy consumption associated with this particular process. There is a lot of raw material wastage in case of traditional technique. Then there is a portability issue as well. You can't take the entire system to somewhere else. These are the limitations of a traditional technique. And what you do is you mimic whatever you are doing in this traditional technique using a microfluidic channel. So what you do is you develop a microfluidic channel and try to mimic the entire process so that it becomes portable. At the same time, it will give you the information associated with that technique. Maybe we'll discuss few things in the coming slides. Then there is another application which is known as organ on a chip. Then in case of biosensors also you use microfluidics. Microfluidics also has an application in analytical chemistry, sometimes in organic chemistry, sometimes organic chemistry as well. In biochemistry also you will find application of microfluidics. Then in physics, of course, you will see different fluid mechanics where microfluidics are used. So this is an example of organ on a chip where the target is to mimic a particular organ. For example, say you want to develop a medicine for a kidney disease. Now, before you try that medicine on a real human being or in any animal, what you do is you mimic a section of the kidney where you think your drug will be mostly active or you are targeting that particular part. You mimic that using a microfluidic structure, and then you can do experiments in that particular microfluidic structure and see what is the different parameters that are influencing in case of that particular drug, so that you can redesign your drug accordingly. Before going to the actual setup, before going to the say human sample or animal sample, you do the same thing in a laboratory setup where you are actually mimicking the portion of the organ under consideration. So in this case, for example, say a kidney has a nephron, and then in a nephron you are mimicking a small portion, and then you know that in this particular small portion there is a tubular flow inside that. So what you are doing is you are mimicking this particular thing into a microfluidic setup. You created a microfluidic channel and then you are trying to mimic the tubular flow, and then you can do or run different experiments. For example, here they have inserted cell, and then they are probably seeing what is the behavior of the cell inside this particular structure, so that they can understand how this particular area of the kidney is behaving in different conditions. Then they'll apply maybe drug, you can apply drug, you can apply different other stimuli to check that what is the kind of consideration that may happen inside this particular organ. So this is one of the examples of organ on a chip, where you are mimicking the organ outside the human body. This has a huge application. As I have said, you can see the behavior of, say, drug, you can see the behavior of cell in that particular arrangement. Now, microfluidic devices are usually made of glass and PDMS. So, glass is a kind of rigid substrate, but PDMS is a flexible substrate, or glass is a rigid material, PDMS is a flexible material. And why we chose these two particular material? Because both of these have a very similar kind of refractive index as well as functionalization. So, it helps us in order to visualize the phenomena from outside. Glass is also transparent, PDMS is also transparent. So, refractive index gives you the idea about the transparency. So, both of the materials are transparent. So, if you create a microchannel using these two material, you can actually visualize the phenomena if you put that microchannel underneath a microscope. Anyways, the microchannels are very small in dimension, it is very difficult to visualize the phenomena with your naked eyes. So, what we do is we develop those devices, and then we put the device inside or underneath a microscope in order to visualize those phenomena. Now, as far as the microchannels are concerned, microchannel can be either closed microchannel, where you have, say, a PDMS block and the microchannel is kind of closed from all the sides, and then you have open microchannel, where you have the substrate present, say it's glass or say PDMS, and then the microchannel is open, that is, top part of this microchannel is actually exposed to the environment. So, you can do experiments in both the setups based on your requirement. You may also find people are making microchannel or microfluidic devices on silicon and other materials. So, here I am just giving you an in general statement. Usually people make microchannel devices or microfluidic devices on glass and PDMS. This helps us to visualize the microfluidic phenomena inside the microchannel. So, microchannel is something which is very closely related to microfluidics. Okay. Now, these are the different types of microchannels that you may find. So, a microchannel can be straight, it can be Y-shaped, where you can actually insert two different types of fluids, and then they will start mixing in this straight part of this microchannel. So, this is called Y-shaped microchannel. Then you have T-junction microchannel, where the inlets, you can use both of these as inlets, and then the fluid will come and enter into this straight part. So, this is kind of T-junction microchannel, this is Y-junction, and then you can also make serpentine microchannel the way it is shown over here. This can be Y-junction in both the sides, it can be T in one side, Y on the other side. This can be serpentine and then a straight microchannel in one side, Y type microchannel on the other side. So, these are the various geometries that you actually can make in a microfluidic device, and the geometries will be decided, or geometries are usually decided based on your application. Okay. So, when you make a microchannel, you also can expose that microchannel to several other stimuli. For example, you can also connect, say, electrodes in both the sides of that microchannel and can apply a high voltage in order to see the effect of electric field in that fluid that is flowing through that microchannel. You can put two different types of fluids and then also can apply a electric field, say somewhere in the downstream, and then can see when they come together whether there is some sort of mixing or some sort of similar phenomena that you may find in case of this type of microchannels or not. Okay, so these are the different types of microchannels that one can fabricate. Now, as far as the fabrication process is concerned, although I will discuss different fabrication techniques in the next kind of stage of this particular lecture series, or next module you can say of that lecture series, but here I am briefly mentioning because some of these techniques probably I will not be able to discuss in that module because these are a kind of different specialized techniques or very specific techniques for this particular microchannel fabrication. So, one technique is kind of laser based, where you can put a substrate in a laser cutting machine or in a laser, or you can expose this particular substrate with a laser, where this laser will create certain sort of mark, and then that particular mark will act as an open microchannel. So, if I take the side view of this microchannel, this may look like this. And then if you want to make a closed microchannel, what you do is you put another similar material and close the microchannel, say using different adhesive technique. Plasma treatment is one of those. So, you can use this technique for creating microchannel. The same technique is also used for E-beam lithography, where instead of laser you use a electron beam. Now, this E-beam lithography technique I will discuss in details in the fabrication section of this particular lecture series, but just to give you an idea that you can also use E-beam lithography technique in order to create such microchannels. Now, one of the problem with laser is the spot size will be in the range of micrometer, but if you need a very small microchannel, for example, say the dimension is less than 200 nanometer, 100 nanometer, then instead of laser you have to use electron beam, because the spot size in that case is even smaller. What is the spot size? If you put the laser on a substrate, the laser will create a spot, so the diameter of spot can be defined or can be described as spot size. So, the spot size in case of laser is in the micron range. So, you actually cannot make a very small channel of say few 100 nanometer or say few 10 nanometer. In that case, you have to depend on an E-beam, and then this is possible in case of E-beam lithography. Then next technique is like if you have a substrate, you put a polymer on top of it, and then you expose UV light through a mask, where the UV can go through this particular pattern, or the UV can go through the other part and cannot go through that particular pattern. That means the pattern is opaque. In this case, this UV will interact with this polymer, and say wherever this UV is interacting with the polymer, this area will become soft, and then if you develop the structure, it will create a Y-shaped structure on top of this substrate. And then if you put another polymer, then this polymer, once it is solidified, you will find after taking out or lifting of this polymer, the same structure is made on top of that, and then this part will act as a microchannel. So, this is nothing but your photolithography technique. I will again explain the photolithography in the coming section. Just to give you an idea, I have shown this particular fabrication technique also in brief here, And then again, if you have an open channel like this, you can put another material on the top and then you can close it. Another technique which is very popular is known as replica molding technique, where if you have a substrate, say you put a small wear on top of it, you put PDMS, you just make a well of say certain material. You can create a 3D printed structure as well, similar to this. Then you put say PDMS with crosslinker. The PDMS will solidify. Once the PDMS is solidified, you take out this particular wear. Then you will find that this wear has created a microchannel inside a PDMS. This is known as replica molding technique. In replica molding technique, the resolution or the minimum dimension will be in hundreds of microns usually, because if you want to go down to say a few tens of microns, then you may find that this replica molding technique is not the best one to use, but this technique is widely used and much simpler. Okay, so these are the different fabrication techniques associated with microchannel fabrication. Some of these will be discussed in the next section. Now, here I have given you some example of microfluidic structure. For example, in the first one, you can see this is a microchannel, and inside that a droplet is moving from left to right. So there must be some sort of inlet through which say two different fluids are coming in. This is a two-phase flow where this is probably one material, the droplet is one material, and the other one is some other material, and then maybe an electric field is applied across this microchannel in the downstream. So this is a video in the downstream. Downstream meaning if you have an Y channel, somewhere here this particular video is taken. So this is downstream, this is upstream, right? So probably here some electric field is applied, and that electric field is actually creating this droplet inside the other fluid. So droplet of fluid 1 inside fluid 2. So this is a two-phase flow, and this is an example of a microfluidic experiment. Then another very important microfluidic consideration is droplet microfluidics, where you study the microfluidic phenomena inside a droplet. So in this particular video, you can see that if you have a droplet of water, and if you expose that droplet of water near a vapor or evaporating material, this will create a huge recirculation inside the droplet, and this recirculation is basically due to the surface tension gradient that has been created because of this vapor exposure. So when the vapor is exposed, so in this area you will find there is a water and vapor interface which changes the surface tension in this particular area, and in this side it's air water interface. So this is vapor water interface and this is air water interface. Now because of that surface tension gradient, the fluid inside the droplet starts moving. So this is known as solutal Marangoni effect, where the surface tension gradient actually creates a recirculation inside the droplet. So this particular recirculation then can be utilized for certain sensing application. For example, say the vapor sensing application only. If you can quantify the movement of this fluid by some means, and then you can quantify the vapor or concentration of vapor, okay, or a particular type of vapor, because this vapor also has a certain value of surface tension. Some other vapor will have a different surface tension. So the surface tension between this vapor and water interface, which will create a certain interfacial tension, will be different from air and water, and this gradient is actually creating this recirculation. So this is another microfluidic phenomena. Similar to that, there is another one where you will be able to see if there is a droplet, and then if you heat it up from the bottom, this also will create certain sort of recirculation. Now because of the heat, there will be two type of or two types of recirculation. First one is due to natural convection, where if you heat up a fluid, you will see that the fluid will start moving up and then again will come down because of this concentration gradient or because of this thermal gradient. And because there is a thermal gradient present, this will create a thermal Marangoni effect similar to that, because this temperature gradient will also create a surface tension gradient, and that will also create a recirculation. So this is a Marangoni convection. So both this convection will be present inside the droplet, and that will also create a recirculation. So this is another type of droplet microfluidic phenomena. This can be used for again a sensing application. So these are some examples associated with microfluidics. Then there is another very important microfluidic phenomena which is known as paper microfluidics, wherein you take a paper and then you coat this paper with some other materials, hydrophobic material. Hydrophobic material meaning this material will, if you put say water, in simpler terms, if you put water on that material, if that material is not getting wet, that means if this water is not forming any film on top of it, then it's hydrophobic, right? So if you put hydrophobic material or some material which will not allow the fluid to spread over, then if you insert a fluid, due to capillary action, you will see that the fluid will move from left to right. So this particular phenomena is known as paper microfluidics. Here capillary action plays an important role. So this capillary force can be tuned, and then you can actually make a device similar to this, where you have different reagents at different places, and then if you put a fluid in the middle, because of this capillary action, the fluid will move towards those reagents, and then they will react with reagents present in these areas. And if it's a colorimetric sensor, they will change color according to the reaction. So from that colorimetric response, then you will be able to detect concentration of an analyte, actually concentration of various analytes. For example, if your material has 7 to 8 different analytes, now for each of these reservoirs, you have coated these particular areas with specific material to different analytes. For example, this is coated with a material specific to A, this is coated with a material specific to B, similarly C, D, E, F, G and H. Then once you put the solution here which has A to H material, the concentration of A to H can be figured out from, or presence of A to H can be figured out from the change in color, okay, because reaction with these specific materials will actually change color of this particular area. So this is a consideration of paper microfluidics, and you can make similar paper microfluidic devices. So this is what microfluidics is all about. I have not discussed the mathematical consideration of microfluidics in order to keep things simpler. Just to give you an understanding that the governing equation associated with microfluidics is Navier-Stokes equation, and then if you also involve electric field and electric potential as a stimuli, then you can use Poisson's equations as well. So these details I have not covered in this particular lecture, because the purpose of this lecture is to give you the idea about different microfluidic sensing applications. In the upcoming discussion, I'll be discussing say sensing examples, so that you understand how different phenomena altogether works for certain sensing. Till then, thank you.